G'day team, welcome back to another video, and today we're going to continue on looking at integration but in a more abstract sense. In the last video we looked at upper and lower estimates using rectangles for my area between two specific points. Now that's really good, but we don't want to be doing that for all of our points that we want to look at. So a bit like differentiation, we can do a general integral, which then we could plug some values in and find our answer. We're going to look at defining an indefinite integral. So a definite integral, like we saw in the last video, is the area under the curve between a specific A and B point. So between A as the lower limit, B as the upper limit. However, if we want an indefinite integral, we're actually not putting that A and B limit on it. We're just looking at the integral function itself. And I also mentioned in the last video that we've actually defined integration to be anti-differentiation. So if I have my big capital F function with my prime of x, so the derivative of big F equals f of x, then the integral of f of x with respect to x equals capital F of x plus c. So essentially, if I differentiate capital F of x, I will get f of x. So if I want to reverse that process, find the antiderivative of f of x, I'll get f of x in return. Now we've got to be careful because this plus c is a special constant of integration, and we do that because hopefully you remember from differentiation, when we take the derivative of a constant term, it becomes zero. So we've got to make sure that we cover ourselves just in case there was that sneaky constant in our original function. Now, just a few rules in regards to integration that will make your life easier. If I have the integral of a constant k times my function f of x with respect to dx, I can pull that constant out the front and calculate the integral of f of x itself. We'll make it a little bit easier down the road. If I have the integral of two functions added together, then I can split those functions up and find the integral of them separately, which again makes our life easier. Now what will happen is you'll see a function like this and just do the integral of both of them individually. And you've just got to remember we are in fact splitting them up, but keeping them in fact together, okay? So we're going to have a look at a little example using differentiation to then find the integral. So I've got a function y, which equals x cubed plus 6x squared, and we want to find the derivative first, so we know how to do that, and then hence find this specific integral of x squared plus 4x dx. So let's start by finding our derivative, so dy by dx. Now this is just a polynomial function, super easy, power rule, 3x squared plus 12x, and that is it. Now what's really cool is if I take the integral of 3x squared plus 12x dx, I know in return I get x cubed plus 6x squared because of my definition of integration and differentiation. So if I find the derivative of my original function, I then throw that into an integral, I get my original function back. Now, it's not quite what we want though. Over here, we are sort of lacking a few things, and I've just realized I missed my 1 there, so that should be 12x, not 2x. You can see I want x squared plus 4x. Now I'm pretty close to that, but I have this common factor of 3. So let's take that out of my function. So if I take 3 away from 3x squared, I'm left with x squared. Take a factor of 3 out of there, I'm left with 4x dx, and that's still equal to x cubed plus 6x squared. So looking at this part here, we can see this matches my integral that I'm after. Now I've got this pesky little constant here, but using my rule above, I can bring that 3 out the front. So we can write this as 3 times the integral of x squared plus 4x dx, and that's equal to x cubed plus 6x squared. Now, if I have something that's multiplied by 3, to get rid of that times 3, we divide by 3. So the integral of x squared plus 4x dx equals 1/3 times x cubed plus 6x squared. And that is the integral that we wanted to find. So my answer is 1/3 times x cubed plus 6x squared. Now you could distribute that through, but we're going to leave it there for now. Awesome. So let's move on to some other rules of integration. Now, essentially, we are using our differentiation rules just backwards. So if I have a constant k, if I integrate that, I add an x to it. So multiply it by x, because when I have kx, or say I had 3x, if I found the derivative of 3x, the x just drops off and I'm left with 3. So I'm reversing that process. If I have x to the power of n plus 1 over n plus 1, I find the derivative of that. I bring the n plus 1 out the front, they cancel out. I subtract 1 off the power, I'm left with x to the n. So for integration, I add 1 to the power and divide by the new power, and that undoes my power rule. However, x cannot equal -1. No, n cannot equal -1. I don't know why I have x there. Let's change that to n. Put a little n in there. N can't equal -1, otherwise this function here becomes undefined. If I have e to the x, my integral is e to the x plus my constant. So all of these have this constant added to it because, like I said before, if I differentiate a constant, it goes to 0. So we need to bring it back in. Now remember, e to the x is the only function whose derivative is itself, which means the integral is also itself. If I have 1 over x, that brings me ln x plus c. So this is the condition where n equals -1. All right, so that goes to natural log. Cos of x goes to sine x plus c, and sine x goes to negative cos x plus c. So that's going to be our basic rules to start with, and then we'll increase that to functions inside of those functions too. So 3 hot fire examples, and we're going to run through them quickly together. So for A, I've got the integral of x cubed plus 4x squared plus 3 dx. Now, if I calculate this, the integral is just those individual terms integrated, added together. So what I can do is, instead of splitting it up, I'm just going to find the integral. So x, now it's to the power of 3, so I'm going to make that to the power of 4 and divide it by 4. So you add 1 to the power, divide by the new power. Plus 4x, 2 becomes a 3, and I divide by 3. Plus 3, because it's a constant, I put the x with it, and plus c on the end. It's as simple as that. If I'm having a look at B, 2 times cos x. Now we can see cos x goes to sine x. So that first term becomes 2 sine x. 2e to the x, well, e to the x stays as e to the x, so that's plus 2e to the x. And because it's an indefinite integral, I add c. Cool. Now, we haven't really looked at something like question C yet, where I've got 2 linear equations multiplied together. Bit like differentiation, we can't, like simple diff, we have to have individual terms and positive, like powers in the top. So what we want to do first is actually expand this out using FOIL. So I've got 2x squared. I'll have -4x plus 3x, which is -x. And I'll have a -6 on the end. So now it's just like part A, and I can go through and do the integral of each term. So x squared, add 1 to the power, divide by the new power, minus x, add 1 to the power, divide by the new power, and 6 is by itself, so I put the x on with it, and I add c. So make sure you've got your functions in a way that you can actually do the integral. Thank you guys for watching. Hope this is helpful, and in the next video we'll extend this idea to functions inside those specific functions as well. Thank you for watching, and we'll catch you then.